Hi everyone, Mrs. V here, and today we are going to do a review of the Bronsted Lowry theory and look at some definitions associated with acids and bases. So let's get our whiteboard on and let's get started. You'll remember our Bronsted Lowry theory of acids and bases that we've already studied, and this year we're going to apply some of our equilibrium stuff that we've learned about to the Bronsted Lowry theory. So this is just going to be a quick review to get you started. First of all, our hydronium ion. We talk a lot about protons when we're talking acids and bases, and what we mean by proton is hydrogen ion. Over here we have a hydrogen atom. So our hydrogen atom, you can see, is just a proton with a single electron. And if we have that hydrogen atom lose an electron, then we're going to get the hydrogen ion, which of course, if it's lost its electron, is just the proton. So whenever we're talking about protons in acids and bases, we're talking about hydrogen ions. Sometimes we write equations with the hydronium ion and sometimes we write equations with the hydrogen ion. I'll show you both as we go through this. So formation of the hydronium ion. When this proton comes in contact with a water molecule, we actually form a coordinate covalent bond or a dative bond. The hydrogen, because it's a positive, is going to be attracted to this spare pair of electrons, this lone pair, this non-bonding pair of electrons on the water molecule. And that attraction is enough to hold the hydrogen atom onto the water molecule. Now, over here we see that the oxygen still has an octet, and we see that this hydrogen has a duet, this hydrogen has a duet, and this hydrogen has a duet. So all of the valence shell requirements have been made for that molecule. The only thing is now, if you count up the number of protons and the number of electrons in that molecule, you'll find out that there is an extra proton. Okay, so there is one less electron than protons, and we say that that molecule is electron deficient. So when we assign a positive charge to the hydronium ion, when we say H3O+, the actual positive charge is on the whole molecule, not just on the hydrogen that's attached to it, not just on the oxygen, but the entire molecule has a positive charge. And that's why we're putting these square brackets here. For once, they don't mean concentration. We're just saying that that entire molecule has a positive charge. So that's our friend, the hydronium ion, and we're going to be seeing a lot of the hydronium ion in our acid and base topic. The Bronsted Lowry definitions of acids and bases says acids are proton donors. So all acids have hydrogen in them, and if it's an acid, it's able to donate at least one of those hydrogen atoms to another molecule. Bases, on the other hand, are proton acceptors. They need something about them that attracts a hydrogen ion. So they are either negatively charged or they have non-bonded electrons so that they can attract a hydrogen ion to them. We've got an example here of HCl. It's reacting with water, and it's going to make, we're going to see that this hydrogen here is going to move over to the water molecule, and that's going to make a hydronium ion, and what's going to be left behind is the chloride ion. We can look at this through an electron dot diagram. When these two molecules here approach closely, because this is a polar molecule, you remember the hydrogen has the positive charge, chlorine has a much higher electronegativity than hydrogen, so it's dragging that shared electron pair over really close to the chlorine. And so the hydrogen's carrying a partial positive charge, which means it's attracted to the partial negative charge of the water molecule. Remember, water is also a polar molecule, and that enables it. Oxygen's electronegativity is a little bit higher than chlorine's. It can actually suck that hydrogen onto the water molecule, leaving, and that means it's left the chloride ion by itself. The hydrogen comes across as H+. It doesn't take its original electron with it. Its original electron stays here with the chloride ion, and we form the hydronium ion. So here we can see that we have an acid. The HCl has donated this hydrogen ion over to the water molecule. The water molecule's accepted it. So HCl is the acid and H2O is the base in this equation. Water is actually amphiprotic, which means it can donate or accept a proton. As we see in our next example, when you put the ammonia molecule with the water molecule, the hydrogen ion on the water molecule can be attracted over to the nitrogen atom. And this forms the ammonium ion, which is, again, an electron deficient molecule and therefore gets a positive charge. And we also leave the hydroxide ion because this hydrogen on the water molecule left without its original electrons. So now the oxygen and the hydrogen have excess electrons. If you count up all the protons and all the electrons in a hydroxide ion, you'll find that there's an extra electron, and this one has not enough electrons. So this one here is electron deficient. Let's have a couple of practice examples. In each 5 of the equations identified the Bronsted Lowry acid and the base. All we've got to do is look at what's happened. If we go to the other side, it's fairly easy to see that these two species are related because they're the only ones with nitrogens in them. What's happened? Here it has a hydrogen, and here it has no hydrogen. So we can see that the hydrogen has actually gone from this molecule over here. So this HNO3 has donated, which makes this the acid, and the one that's accepted is the base. Next one, again, have a look, and we can see that this one is related to that one because they're the only ones that have fluorine atoms in them. What's happened? This one has an H, and this one has no hydrogen, which means that this has donated its hydrogen to the water molecule. So this is your acid, and this is your base. Okay, some definitions: ionisation and dissociation. Ionisation is a reaction that produces ions, usually from neutral molecules, whereas dissociation is a process where a compound splits up into its ions. Now, unfortunately, in the topic of acids and bases, we tend to see these two words used interchangeably, but I want you to rise above that common error of interchanging those terms. Ionisation and dissociation are different. In ionisation, we produce ions from neutral molecules, but dissociation, the ions are already there in a lattice and they have broken up into their separate ions. Let's have a look at a couple of examples. So in our ionisation of HCl, you can see that here we have a neutral molecule of HCl, no charges on it, and we have a neutral molecule of water. And over here, we have ions. So we have turned neutral molecules into ions. And that is what we call ionisation. Ionisation. Have a look at this second example in which sodium chloride dissolves in water. Here we have the ions already. So they're already present. All we did was separated them. That is what we call dissociation. Now, there are some interesting examples in acids and bases where we react an ion with a water molecule. Let's have a look at one of those. If we, for instance, had the ammonium ion, and we reacted that with a water molecule, then we could get ammonia and the hydronium ion. Now, this still counts as ionisation because we took a neutral molecule and we turned it into an ion. We also took an ion and we turned it into a neutral molecule. So even if we've got a mix of ions and neutral molecules, if you've turned neutral molecules into ions, then that is ionisation. Do you remember conjugate acid-base pairs? When an acid donates its hydrogen ion, the bit that's left is the conjugate base. And when a base accepts a hydrogen ion, then what's left is its conjugate acid. So conjugate acid-base pairs differ by H+. So you have your acid and your conjugate base. Whoops. Losing a proton, gaining a proton. If we have a look, in this example, water acting as an acid, we remove its H+, and we end up with the conjugate base of the hydroxide ion. Ammonia, the base, we add H+, and we end up with the ammonium ion. Let's have a quick practice. All you've got to do, pause the video, and I want you to decide what is the conjugate base or what is the acid for each of these species. And I've even made it easy for you. You've got a word box. Well, it's really a formula box. Have a go at those. Come back and find the answers. Okay, HCl. It's an acid, so when it loses its H+, what's going to be left is Cl-. You can see when an acid donates a proton, it goes down by a hydrogen and down by a charge. So bromide is the base. What will be its acid? Well, if you go from the base to the acid, you go up by a hydrogen and up by a charge. So it's Br-, so we go to HBr, and the charge goes up from -1 to 0. Acetic acid or ethanoic acid, we need to take it down by an H and down by a charge. Now, interestingly, only this hydrogen is acidic. These ones are not, because if you draw the formula of this, it looks like that. What we have here is a delta minus delta plus. The charge separation along there allows that hydrogen to be lost. But these bonds here are pretty non-polar. So they're not as easy to break. So there's only one acidic hydrogen there. So this is going to make the acetate ion. OH minus, the acid, its conjugate acid is H2O. H2PO4 double minus, if you take a hydrogen off, you'll end up with PO4. If you go down by a charge from 2 minus to 3 minus. HSO4 minus, if you go up by a hydrogen and up by a charge, you get H2SO4. Over here, NH3, to find its conjugate acid, to go from the base to the acid, you add a hydrogen. So it's going to be NH4, and you go up by a charge. CH3, NH3 plus. To get back to the base, you're going to need to lose a hydrogen and go down by one charge. So you're going to end up with CH3, NH2. Cn minus. To go over to the acid, you're going to have to go up by a hydrogen and up by a charge. H2PO4 minus. To go to the base, you're going to need to lose a hydrogen and go down by one charge. H2O, to get to its conjugate acid, you're going to need to add a hydrogen and go up by one charge. Hydrogen iodide, to get to the base, you're going to need to go down by a hydrogen and down by a charge. How'd you go with those? Make sense now? Next definition, polyprotic acids. When we're dealing with acids and bases, we quite often use these very general terms for an acid. A monoprotic acid has one proton or one hydrogen in it. A diprotic acid has two, and a triprotic has three. Now, these have to be acidic hydrogens. Technically, acetic acid has 4 hydrogens, but only one of them is acidic, so it's monoprotic. Let's have a look at what that means. Monoprotic donates 1 proton per acid molecule. HCl we've seen before as an example, HNO3. You can see that it's making 1 hydronium ion per acid molecule. You could write this, a sort of simplistic way to write the monoprotic thing is to actually just use H plus and leave the water out of it. And you'll see acids and bases worked in this way from time to time. I think we can, at year 12 level, use H3O plus. All right, polyprotic acids, diprotic, triprotic. A diprotic can donate 2 protons per acid molecule. And our classic example for this is sulfuric acid. And we see here the simplistic idea that we're just breaking it up into H plus and HSO4 minus. But the HSO4 minus still has an acidic hydrogen. So that can go further and it can make another hydrogen ion and another sulfate ion. Oh, sorry, and the sulfate ion. What we can do is write that, let's write that, let's be grown-ups about our acid-base work. Let's use the reaction with water. And then this still has an acidic hydrogen, this HSO4 minus, hydrogen sulfate ion. So that can react further with water to make the sulfate ion and another hydronium ion. So overall, what's happened is that the sulfuric acid has reacted with 2 water molecules to give you the sulfate ion and 2 hydronium ions. Now, when you're asked to write equations for showing diprotic nature, you should write the two separate steps. Not in sulfuric acid and in many acids, the second ionisation step only occurs to a small extent. And we're going to be talking about that later. All right, triprotic acids donate 3 protons per acid molecule. Here we're seeing the classic example is phosphoric acid, H3PO4, and we're seeing its first ionisation step. And this is written simplistically as well. In fact, I would prefer you to write H3PO4 reacting with water, showing that you go down by a hydrogen, down by a charge, and show the hydronium ion instead. Okay, and you can go through and do that for the second 2 ionisation steps. And again, we see that the first dissociation occurs really well, but the others to a much smaller extent. Okay, that's all we need to say about our review. We are going to be continuing our work with acids and bases and looking at how equilibrium considerations can be applied. But for now, I'm going to see you in the next video.